My name is Pranav Giraju, and this is Physics Lab 2 Projectile Motion. The purpose of this lab is to analyze the projectile motion of an object and compare experimental results with computational models. We do this by capturing a video of the motion, then analyze the video using the tracker software to extract the object's position and corresponding times. In this lab, we use the duster as the object of observation. The duster is a system in this context. Throughout this lab, we are directly applying Newton's second law of motion, or the momentum principle. Additionally, gravitational force and drag force is also applied. Newton's second law of motion states that the rate of change in momentum is equal to the vectorial sum of forces on a body. Gravitational force is the force that pulls objects with mass towards each other, and drag force is the force that resists the motion of an object. Here you can see are the relevant equations: change in momentum, position update, velocity update, drag force, and gravitational force. Here you can see is a preview of the results from this lab after using the tracker software and GlowScript to create graphs. I will elaborate more on this after explaining the experiment. First, we recorded a video of the duster falling in a projectile motion for use in the tracker software. Then, using the tracker software, I tracked the position of the duster frame by frame in an interval. Then, I got the data from tracker and imported it into an Excel file, where I obtained the x versus time graph and y versus time graph. And finally, using the starter code provided, I created a computational model based on the physics principles. One that included only the effect of gravity and another that included both gravity and drag. Here you can see is a screenshot of the tracker software where we use the center of mass markings to track the duster's projectile motion to create the two graphs you can see on the right. Then, here's the starter code provided for GlowScript where we modified several of the values and determined both the gravitational force and the drag force, and subsequently the net force to be used for the computational model. Here's the x versus time and the y versus time graphs that were obtained after running the GlowScript program. And here's the computational model of the trajectory of the object that was thrown. Finally, here are the final graphs. On the left is the x versus time graph, and on the right is the y versus time graph. On the left graph, the solid blue line represents the tracker data, while the green line represents the computational model with drag force, and the dotted line represents no drag. Meanwhile, on the right graph, the light blue line represents the tracker data, while the solid blue line represents a computational model with drag force, and the dotted line represents no drag. As you can see, there is a significant deviation when it comes to the graph obtained by the tracker software, as compared to the drag and no drag graphs obtained to the computational model. Sources of error. Various other external forces are at play that may have been unaccounted for. Any external sources of air or wind that may have hindered the projectile motion, for example, fan, AC, etc. Errors within the position tracking software, and camera angle issues. What does it mean and what if? Do any of your models predict the terminal velocity? No. None of my models predict the terminal velocity. In order to determine the terminal velocity of an object, we could design an experiment in which an object is thrown from a height and measure the v versus t graph and determine terminal velocity. What if the object were thrown vertically upwards with the same initial speed? Then the time to hit the ground would be longer than in the original experiment. This is because the object must first slow down to a complete stop at its highest point before it can fall back down. This extra phase of motion increases the total time in the air. Thank you.